In this video, we learn how to determine the rate law using two methods, the integration and the half-life method. In prior videos, we have defined what the rate law of a chemical reaction is. And the rate law is simply how the rate of the reaction depends on the concentration of reagents. So for a reaction A to give products, we can always write the rate law as this. Rate, which is defined as the change in concentration of reagents as a function of time with a negative sign, is going to be equal to a common expression in which you have a proportionality to the concentration of that reagent to some power that you have to determine. Okay, so we have seen that this expression is very useful in the integrated version, in which if you know the rate constant and the order of the reaction, then you can come up with ways to figure out how the concentration of reagents disappears as a function of time. And those were the integrated rate laws. Right, so what we're going to learn to do here is actually how to determine what this order is, x, and what the rate constant is. Okay, so again in this video we're going to see two methods to determine the rate law. First is the integration method, and then the half-life method. Right, so what is the integration method? The integration method simply consists of using the integrated rate laws to see if the variation of the concentration of reagent as a function of time matches with what we know for a given order. So for example, if the reaction is first zeroth order, okay, we actually know that the integrated rate law is equal to the concentration of A is equal to the concentration of A at time 0 minus K sub T. For a first order reaction, we know that the way that the concentration changes on time is like this, minus KT. And then for a second order reaction with one reagent, the way the integrated rate law is like this, 1 over A naught plus KT. And again, that will be for a zeroth order reaction, that is for a first order reaction, and this is for a second order reaction. Something that is common in these expressions is that they all depend linearly on time. So doing linear fits to this expression could be fairly simple. For example, the way to make a linear representation of this expression is to plot time in the y-axis and the concentration of A in the x-axis, time in the x-axis, and the concentration of A in the y-axis. Okay, and that means that this should be the equation of a straight line, where A naught is the intercept with the y-axis, and the slope is equal to minus k. Right, so you have a representation that looks like this, where the slope is equal to minus k. Right, so then you can determine the rate constant and the order of the reaction if you take measurements of the concentration of A as a function of time, and then if you represent them like this, and you have that, you see the linear fit fits well your data. Again, you will be measuring the concentration of A as a function of time, and then you can represent that. If this fits quite well, then you can determine that this is a zeroth order reaction, and then the slope you can determine from the rate constant you can determine from the slope. Okay, and again you can proceed the same way with the first and second order reaction. We're just going to plot here how those graphs look like. Again, you always plot time in the x-axis, and then in this case, to make sure that you have a linear representation with respect to time, then in the y-axis you will need to represent all of this. Okay, so that would be mx plus A. In this case, the intercept with the y-axis will be 0. So here you represent the natural log of the concentration of A over the concentration of A at time 0. And again, that should be the equation of a straight line, okay, where the slope is also minus k. Okay, and the intercept with this axis, with the y-axis, would be 0. For a second order reaction with one reagent, again, time appears in the x-axis, and then you would represent 1 over A in the y-axis, and your representation would be y is equal to A plus mx. Okay, notice that in this case, because the rate constants are always positive, all right, this data should have a positive slope, which is equal to the rate constant. Okay, and the intercept with this axis would be equal to 1 over A naught. And the slope is equal to k. All right, so again, that's the way to figure out where the reaction order and the rate constant is for in a reaction. Again, what you will do is try to measure concentration of A as a function of time, and then you would do 3 plots. Okay, in the first one you would plot directly A in the y-axis, time in the x-axis, and see if this fits nicely to a linear fit. To determine whether this is first order, then you would plot the natural log of the concentration of A over the concentration of A times 0, plot it as a function of time, and if it fits well, then the slope should be minus k. And then for a second order reaction, what you would plot is the inverse of the concentration of A as a function of time, and again see how good the fit is, and that's how you determine the slope. Okay, so this is a nice method, an easy method, okay, which it has one disadvantage though, and that is that it would only work if you actually have that the reaction order is either 0, 1, and 2, but that's not always the case. There are reactions that might have a negative order, fractional order, so we haven't seen the integrated rate laws for any of those cases. We have only seen the integrated rate laws for the 0th, first, and second order reaction with one reagent, right? So this method seems to be a little limiting, even though it will work very well if you suspect that the reaction order is either 0, 1, and 2. Okay, so that is the integration method to determine the rate law. Notice that again, you will be determining whether this is 0, first, or second order reaction from the quality of the fit to each one of these expressions. Okay, and then the rate constant can be obtained from the slopes of the expressions. Right, the second method that we're going to see in this video is the half-life method. Right, so an idea then would be to notice that the half-life for 0, first, and second order reactions has varying dependencies on the initial concentration. Okay, so for example, we have seen very clearly that the half-life of a first order reaction is very interesting because it shows no dependence on the initial concentration. And we know that T1/2 is equal to the natural log of 2 over k. Okay? Now we could derive the half-life expression for a 0th and a second order reaction, and the way to do this would be to simply take the integrated rate laws and then replace the concentration of A by the concentration of A at time 0 divided over 2, okay, and then T by the half-life. Solving by the half-life, you will get the expression for the half-life for 0th order or second order. Again, you would replace this by A naught, A at time 0 over 2, and then T by T1/2, the half-life, and that will give you the expression for the half-life. Right, so if you were able to do that, what you would find is that for a first 0th order reaction, this is equal to the concentration of A at time 0 over 2k. And for a second order reaction, what you actually find is that the half-life is equal to 1 over A naught k. Right, so if you have a method to determine the half-life, if you can measure the half-life in your chemical reaction, then it's very easy to tell apart whether this is 0, first, or second order reaction, right? It turns out that the half-life for a first order reaction should not depend on the initial concentration. For a first order reaction, it should depend linearly, and then for a second order reaction, it should depend inversely. Something that is interesting about this half-life method is to notice that there seems to be a dependence of the power of this half-life on the concentration of reagent. Notice that when you actually have 0th order reaction, then the power of A to the naught is 1. Then when you have a first order reaction, the power to the A naught is 0. And when you have a second order reaction, the power of the A naught is -1. Okay, so actually this is something that is universal. We haven't looked at third order reactions or fourth order reactions, but those would all kind of follow along this trend. So for a third order reaction, you will have that the half-life will depend on the inverse of the initial concentration squared, and so forth. Okay, so again, that is the two methods, two of the methods to determine the rate law for a chemical reaction with one reagent. We have seen the integration method, we have seen the half-life method. Both are useful. The integration method is probably a little bit easier to use, but the applicability is not universal. Notice that we can only use these methods if we actually suspect that the reaction is either 0th, first, or second order. In the next video, we're going to see methods that are a little bit more universal, and they would allow you to determine the rate law even if the reaction order is non-integer or negative, or it has no restrictions.